Hello, welcome back. This is going to be part 2 of my demonstration video series on the design and simulation of flat panel or distributed mode loudspeakers using my software PETTaLS, which stands for Perfect Exciter and Tactile Transducer Loudspeaker Simulator. This video is going to be about exciter placement and the use of multiple exciters on a single panel loudspeaker. If you haven't watched part 1, which was the introduction to my software, I would suggest that you probably go back and watch that because I go over what all of the different graphs mean and what all the different design metrics and parameters are used for in the software. So in this video, I'm going to be talking about exciter placement and installation mostly, and I'm going to use this Parts Express Exciter Buyer's Guide as a reference. This has some information on the different types of exciters that are available and different materials that you can use, and then exciter placement and installation. They have suggestions on where to place 1 exciter, 2 exciters, and 4 exciters. For the placement of 1 exciter, they say good results will be given with the exciter mounted distance of 2/5 from the panel width from one side of the panel width from one side of the panel and 3/5 from the other side of the panel, with the same relationship used for exciter placement with respect to the panel height. This relationship will provide a satisfactory offset to reduce the buildup of standing waves on the panel. The diagram here, like, this is clearly not 2/5 and this is not 3/5. This is probably more like 30%. So I'm going to use the picture more as a guide than the numbers here. So I'm going to call this 60% and I'm going to call this 30% from the lower left corner. What they mean when they say this relationship will provide a satisfactory offset to reduce the buildup of standing waves is that if you put an exciter right in the middle of the panel, you're going to be exciting a pretty narrow subset of modes, because there are a lot of modes that have a node right in the center of the panel, and so you're not going to excite those modes at all. And so placing the exciter off-center is going to excite more modes because there are fewer nodes off-center. And that does have an effect on the frequency response. So let's compare those two placements with 1 exciter and see what they look like. I'm going to use point force exciters for right now. Point force exciters are ideal exciters, which have no low frequency effects from the resonant properties of the exciter and no high frequency effects from the shape of the exciter. By neglecting those things, we can just isolate the impact of the location of the exciter without caring about how the actual resonant properties of the exciter affect everything. But I will show realistic exciter results later. So let's put that 1 exciter right in the middle of the panel, 0.5, 0.5. I'm going to use simply supported boundary conditions for right now. That's going to match this compliantly suspended panel edges, edge termination and damping setup. I have the ability to simulate other ones, and I'll show a different example later on of the same thing but with different boundary conditions. No stands. I'm going to use a 0.2 meter wide by 0.3 meter high panel of thickness 6 millimeters and acrylic. I like this one because it simulates relatively quickly. Okay, I'll be back when the results are in. Okay, we've got our results. Up here in the upper left, we can see our panel dimensions and the little point force in the middle, if you can see that little dot. In the middle graph here, we have the surface velocity of the panel, and I can select different frequencies. It's not going to change much until I get to these higher frequencies. Because the exciter is right in the middle, can I get rid of that dot? No. Because the exciter is right in the middle, I am going to get these really symmetrical vibrational shapes, and then they become isolated around the exciter at high frequencies. Yeah, pretty neat looking. Trippy. Here's the frequency response. The dotted line is the frequency response of the surface velocity. The solid line is the acoustic frequency response at the horizon level. It's from minus 90 degrees to 90 degrees, infinitely baffled. The red line is the coincidence frequency. That's when the bending wavelength on the panel is equal to the wavelength in air, and the radiation starts beaming from the panel edges. Usually there's a little increase in radiation, average radiation, around that frequency, and then it starts to decrease after that. You can see in the acoustic frequency response that there's definitely a lot of sharp peaks and troughs in this. That just indicates that we don't really have the best exciter placement. If we move that exciter off center, we'll be able to mitigate those effects a little bit. So let's move this to the off center exciter, which I said was 0.6 and 0.3, and then we'll compare those to these original results. All right, we've got the new set of results there. You can see here in the velocity frequency response, the new dotted line has more peaks than the old line did. And we've filled in some of those troughs here in the acoustic frequency response. It's a little smoother. Still not like the smoothest thing in the whole world, but it's a little smoother. I would zoom in, but I'm having trouble with the zoom functionality. It tends to really go haywire. So for right now, I'm not going to do that. You can just see, though, that this dotted line is a little smoother. The peaks seem to be a little less distinct now. If I look at the surface velocity map, the patterns are a lot less symmetrical, less trippy. And then the vibrations become isolated around the exciter at high frequencies. Yeah. Okay, so the next thing that I want to show is a corner exciter. So let's do a new simulation from scratch, and let's put this exciter in the corner. By putting the exciter in the corner, you can actually excite the biggest possible subset of modes. If the exciter was as far in the corner as possible, there are no nodes there, except at the exact corner, but close to the corner there are theoretically no nodes, so you would be exciting all the modes, but this doesn't work as well as you would think. So let's look at that output from this. All right, cool. Here are our results for the corner exciter. You can see that exciter's down here. Yeah, surface velocity is probably going to tend to be kind of isolated down there in the corner a lot of the time. Yeah, this is kind of funny down here. You do excite more modes this way. You can see probably in here that there are a lot of modes being excited. Not all those modes are very efficiently radiating. Like this one doesn't radiate at the horizon at all. That's because it is, let's see, what frequency is that? 332. That is this mode. And there's the horizon, which is canceled out by these two. So no radiation there. One thing that placing the exciter in the corner definitely does is reduces the low frequency output. Those low frequency modes are just not excited very efficiently. So let's compare that to our off-center placement, 0.6, 0.3, and we'll be able to compare those two outputs. All right, there we've got our comparison. You can see, if I move this out of the way, the off-center exciter is the dotted line here. A lot more low frequency output and smoother at low frequencies too. So I wouldn't recommend corner placement, really. It just doesn't work very well, to be honest. For the next set of simulations here, I'm going to look at two exciters now. Going back to the Parts Express guide, they have this recommended two exciter placement, and they say if multiple exciters are needed for a panel surface, it is not recommended to space the exciters evenly across the surface. This will result in very narrow sound dispersion at upper, mid-range, and treble frequencies. Instead, place the exciters together in a group with exciters at unequal distances from the panel edges and from one another. Okay, so let's compare some of those things, and I'll talk about the results that happen with the two different setups. So going back to the simulation software here, I'm going to uncheck compare results so I get new results. I'm going to check exciter 2 so I get a second exciter. I'm going to put two exciters at sort of evenly placed locations, 0.5, 0.33, and 0.5.67. Same boundary conditions, same panel and everything besides that. Still 0.46 exciters right now. So let's take a look at those results. Okay, here we've got our results. You can see the two equally placed 0.4 dots here. Yeah. Surface velocity map is going to have a bunch of symmetrical modes, and then as we get up in high frequencies, it's going to be all just where the exciters are. So, an interesting thing happens when you symmetrically place exciters, which is that you excite a really narrow subset of modes. And that's actually kind of good at low frequencies because we have one peak and then a fairly flat response here up until about a kilohertz, it looks like. And then we get these really sharp peaks and troughs. So when Parts Express said that you get narrow sound dispersion at mid and high frequencies, I think what they're referring to is the fact that you get these really sharp peaks and troughs that have these pretty characteristic and noticeable polar dispersion patterns. And then here is the coincidence frequency that starts beaming. That's going to happen regardless of what exciter placement we use. So that's kind of an interesting output, actually. You can, if you want that sort of sound, you can get that using equally, like equal exciter placement. But let's compare that to exciters that are spaced more closely together. So I'm going to do 0.6, 0.3, and let's do 0.7, 0.2. That's far enough apart, and we'll compare that to the old results. Okay, so the two exciters are now placed more closely together towards the corner. We're going to get not very symmetrical shapes on the panel surface that are going to be kind of isolated up here at the high frequencies. And you can tell in the vibrational frequency response we have way more modes being excited. Some of those modes don't radiate at the horizon level, but we have definitely more going on in here on this dotted line. And it's hard to see because I'm having trouble zooming in on this GUI right now. But a lot of these really sharp peaks and troughs in the solid line are a little smoother in the dotted line. So yeah, the two off-placed exciters or off-center exciters that are close to each other have, maybe a less flat low frequency response, but a more flat mid and high frequency response. So it's kind of a trade-off. And you can see that the polar radiation stuff here is a little more chaotic, maybe? Diffuse might be a better word for it. It's not quite filled with such sharp peaks and troughs as it was with the centrally placed exciters. So I came up with something in, what was it, 2015 or so, called a modal crossover network, where you use equally placed exciters for the low frequencies and then a crossover network and then these off-center exciters for the high frequencies. And so I haven't built something like that into this software yet. And I also have a patent on that. So as far as I know, it's not being used in anything right now. But I do have a patent on that, so I'm not sure anybody else but me and my colleagues can use it for the time being. Okay, so the next thing I wanted to do was compare these two sets of results, but using real exciters. So I'm going to redo that first simulation, 0.5, 0.33, and 0.5, 0.67, but using real exciters, just to see how this changes when I am no longer using point force exciters. So let's take a look at that. All right, there's the results with the real exciters and the equal placement. Again, looks kind of similar. Maybe the high frequency stuff is a little different. A lot of this is probably going to drop off a little faster than before, and then we've got this extra little peak due to the resonance of the exciter, and then it drops off pretty steeply at low frequencies. So let's look at the off-center grouping now with the real exciters. All right, the dotted line here is the set of results for the two grouped off-center exciters. Similar to the point force exciters, we've got less flat low frequency response, but again seems to be more smoothed out high frequency and mid frequency response. So trade-off. Okay, for the last set of simulations, I want to look at 4 exciters. Parts Express has these example layouts for 4 exciters. There's one where the exciters are in a row and one where they're kind of grouped together. And we're going to compare those to 4 equally spaced exciters on the panel surface. I just did a simulation and I forgot to check exciter 3 and 4 on, so it only simulated 2 exciters. So I'm going to redo this. The exciters are back to point forces and equally spaced. So I did 0.33, 0.33, 0.33, 0.67, 0.67, 0.33, and 0.67, 0.67. So we'll get rid of these results and look at the 4 equally placed exciters. Mamma mia. Okay, there's our results for the 4 equally placed exciters. You can see them here. It's going to be symmetrical patterns on the panel surface, and up at these high frequencies it's going to be mostly isolated around the exciters. Wow. So we've got a nice area here of broad omnidirectional radiation. That comes from the fact that for a long time, up until about a kilohertz, we have kind of nice radiation patterns, and then after a while it gets screwed up in here. The low point in the radiation is at 1600, so that's this mode roughly. Yeah, interesting. So we get a nice low frequency response. This peak could probably be equalized out, and we get a nice low frequency response followed by a pretty abysmal mid and high frequency response with a lot of sharp peaks and troughs. So that's why they say to avoid this. Even though the low frequency response is good, the high and mid frequency response is pretty awful. Okay, I'm going to now try to simulate this one, and I don't have the exact placement of these exciters, but I'm going to try and just guess where they are. I'm going to use 0.6 and 0.3 as the location of the first one, and then they increase in Y value by quite a bit and increase in X value by only a little bit. So I'm going to do 0.65, 0.4, 0.7, 0.5, and 0.75, 0.6 for this one. And same parameters, otherwise we'll compare that to the equally placed exciters. Hey, look at that, not too shabby. So we got maybe a slightly worse low frequency response because more modes are being excited, but you can definitely tell that that mid frequency response is a lot more smooth in here. This huge trough is no longer there. That's because we're exciting a lot more modes. So that pattern looks pretty close actually to this pattern. I think I did a pretty good job estimating that. So yeah, it doesn't really become super isolated, but here's what it is. Let's compare that to this exciter placement now. So I'm going to go back and redo the first placement, and then we'll compare that to the second layout. Okay, so now I got to try and estimate what these would be. This first exciter looks like it's the same thing, which I'm going to call 0.6 and 0.3. And then the next one is going to be the same X location. And let's see, a little higher up. So maybe 0.43 or something. Then this one is farther over. Let's call it 0.73. Let's just say. And then 0.37. I'll call this, and then 0.73. And let's see, so I added 13 here, so I'll add 13 here. That's 0.5. Hopefully that looks right. Let's see. Yeah, that looks pretty good. That's probably about right. sort of isolated around there. Yeah, you can tell where the exciters are in some of these patterns. Like this one, I can see the 4. And again, probably worse low frequency response with more peaks, but we've smoothed out a lot of the really sharp stuff in the mid and high frequencies. Mids especially. Those mids were pretty terrible with the 4 equally spaced exciters. Comparing this to the other layout in the row of the 4 exciters, I'm not sure. I don't want to make this video 100 million years long, so I'm not going to compare those two. I'm not sure exactly how they compare, but they don't seem super different to me. Okay, the next thing that I wanted to do was show 2 4 exciter layouts, but with real exciters. So let's go back to real exciters, and I'll redo these 2 simulations. Okay, there are the results for the 4 real exciters, equally spaced. They've added this extra bump at low frequencies and it drops off more sharply. And it probably drops off a little faster at high frequencies than the point force exciters did because of the shape of the ring of the exciter. So let's compare that to the, let's see, 0.6, 0.3. I only remember the numbers that I put in for the line, so I'm going to redo those. 0.4, and then 0.7, 0.5, 0.75, 0.6. All right, there's the 4 real exciters in a line on the panel. Yeah, we've same basic set of results as the point forces. We've got a maybe slightly worse low frequency response with more peaks. Let's see, what's going on here? Let's try to find that frequency. 563. That's probably this, something weird going on there. And then, but we've smoothed out some of these really sharp peaks and troughs at the mids. So, yeah, I don't know. I don't know which one's better. It's totally up to you. Trade-offs. Always trade-offs. So I had a few more simulations that I wanted to run, but I have a feeling this video is already long enough, so I'll save some of those for subsequent videos where I'll be exploring different boundary conditions and different panel materials and different panel dimensions. I'm not going to do that here because it's just too much. Okay, thanks.